This is Shane Picard with another geometry video. Today we'll be talking about similarity transformations. Transformations generally are movements of or changes to an object. Generally, transformations are observed in the coordinate plane. That is to say, when we look at or when we analyze transformations, we typically place them into the coordinate plane. The reason is that it allows us to quantify the transformation. That is, it allows us to put numbers to it. So we can distinguish between a transformation where something is moved 6 units to the left as opposed to one where it's moved 8 units to the left, or where an object is rotated 90 degrees as opposed to 180 degrees. The coordinate plane allows us to do those quantifications. Today we're talking about dilations particularly. Dilation makes a figure larger or smaller. Think about the pupil of your eye, how it dilates, that is, it gets bigger or smaller. We talk about dilations in the geometric context. We're talking about exactly the same thing, an object getting larger or smaller. Since a dilation results in a new figure which has the same shape as the original, even though it is a different size, we refer to a dilation as a similarity transformation. Why similarity? Well, because the two objects have the same shape. Take a look at this square. The square is some particular size on the screen, and we can dilate it, we can make it larger. There's a couple of things we need to be aware of as we see the object dilating, getting larger and smaller. A couple terms we should be familiar with. First of all, the image that we start with is actually called the preimage. The preimage, or the before image. After it's dilated, we get some final image. Call the final image, well, call it the image. So we have a preimage and an image. Every single point in the image was in the preimage. So in this example as it's drawn right now, you can see the preimage has the diagonals drawn in. In the image, the diagonals are not indicated. I can indicate them, like so, but my failure to do so doesn't mean they're not there. I simply didn't draw them. But notice that there's really an infinite number of points in the preimage. And correspondingly, there's an infinite number of points in the image. It's important to keep that in mind. When we work with these concepts in geometry, however, we always work with a fixed number of points, and it's usually a relatively low number. We'll label these points A, B, C, D, and the intersection of the diagonals we'll call E. So we have these 5 points that have been brought to our attention. When we take the preimage and dilate it into the image, whatever size it happens to be, we will rename these 5 points. So for instance, suppose we dilate the image so that it looks like this. You can see the image has gotten quite a bit larger. We'll put the diagonals in. There they are. When we name the points in the image, we will refer to them by their former names. For instance, this is B. But we will append the word prime. This will be called B prime. So this letter, followed by what looks like a single quotation mark, is read B prime. In other words, that quotation mark is read prime. So this is B prime. This point up here is C prime. This point in the lower right corner is D prime. And at the intersection of the diagonals, we have E prime. So that is some notation that's important for us. You'll notice, based on the way I chose to dilate this object, that is this square ABCD, you'll notice that this A, point A, appears to be in the same place as A prime. So that point has either name A or A prime. Normally, we wouldn't need to rename A to A prime. We simply refer to it as A, because it's the same point and it hasn't moved at all. So we do have prime, C prime, D prime. We have point A at the same place as the dilated vertex would be. And we would refer to the new square as square A, B prime, C prime, D prime. We refer to those points by their new names anytime we want to bring attention to them. The only reason we reuse the letters is simply that it makes it very easy to figure out which points correspond to each other. C prime corresponds with C, D prime corresponds with D, so forth and so on. So we have an image, we have a preimage, we have new points which are called the prime points, B prime, C prime, etc. We also have a couple other features of this shape, which maybe are not obvious, but we should talk about them. The first one is called a scale factor. We've already looked at that term in prior sections. Scale factor is the number which I would multiply by any value in the preimage to obtain a corresponding value in the image. So for instance, if segment AD were 1 inch and segment AD prime were 3 inches, then my scale factor must be 3, because I've taken the value of AD and multiplied it by 3 in order to produce AD prime. Likewise, I would find that if BC were 1 inch, then B prime C prime must be 3 inches, because the scale factor is 3. So that's the first thing we need to be aware of, is the scale factor. The second thing we need to be aware of is what we call the center of the dilation. The center of the dilation is the point about which dilation takes place. That is the point about which the dilation expands. If you think of a touch screen, you probably know that the place on the screen where you place your finger and thumb in order to zoom in is sort of the point of dilation. Everything zooms out from there. So if you're on a map, for instance, and you zoom in around Boston, Boston stays in the center and everything else moves out from there. If instead you zoom out from Providence, well, Providence stays in the center and everything moves out from there. So the center is the point about which everything expands or contracts. In other words, the center is the one point in the dilation that doesn't actually move from preimage to image. And in this particular example on the screen, you can see that point A is the center. Point A is the only point that didn't move from preimage to image. Everything else moved away from point A. So again, we call that the center. Take a look at another object here. This object is also two-dimensional in the sense that it's on the screen. It appears to be three-dimensional. The only reason I've included this object is to show that any two-dimensional object or drawing or diagram can be dilated exactly the same way. It doesn't matter how complex or how simple it is. It could be anything from a segment to a more complicated image such as this one. I mentioned that all dilations have a center and a scale factor. The center, again, is the point of reference, while the scale factor quantifies how much the figure stretches or shrinks. Let's look at this example. It says dilate rectangle KLNM with center at point M and a scale factor of 2. The center is here at M, so that's the one point in the image that won't move. In other words, M prime, if we were to label such a point, is the same as point M. So, we need to deal with the scale factor. It's important to recognize that the image and pre-image of every point in the diagram will always lie on a ray, with which ray has endpoint at the center. All right, that's a little bit hard to get our head around. Let's take a look at what I'm saying. We have point N here, and we have point M. We're just going to focus on point N, and we'll pay a little bit of attention to point M. Forget the rest of the diagram for a minute. What I said is that the image and the pre-image of every point lie on a ray with endpoint at the center. So because M is our center, I know that there is a ray that exists called ray MN, goes in this direction, not the straightest line in the world. And I also know that N prime will be somewhere on that ray. Let me say it again. Every image and pre-image will lie on a ray that has the center as its endpoint. So I've got this ray MN. I know that N prime will be somewhere on that ray. The next question we need to ask is, well, where will it be on the ray? Well, in order to find that, I take the distance from the center to the pre-image, and I multiply it by the scale factor. In other words, N prime must be twice the distance from M as N is. So these two segments are congruent. Now, I'm not suggesting that in every dilation those segments will be congruent. They're only congruent here because I have a scale factor of 2. To show that differently, I can write that M, which is my center, N prime is equal to my scale factor times Mn. Mn prime is equal to my scale factor times Mn. Let's move on now and talk about point K. Again, we find that point K and point K prime will be on a ray, and that ray will have M as its endpoint. So we can begin to draw the ray MK. We know that point K prime will be somewhere on that ray. We need to ask the question, well, how far from M will the point be? All we need to do is take MK and multiply by the scale factor of 2. That tells us that point K prime will be twice as far from M as K is. This is K prime. We'll do the same thing with point L. We take a ray that goes from M through L. We know that L prime will be twice as far from M as L is. Somewhere in this neighborhood, that's L prime. And so now we can see that we have scaled these 3 points. Notice we scaled the points without respect to the rectangle itself. I wasn't really paying any attention to the rectangle. I was focusing 1 point at a time. Now that I've found N prime, K prime, and L prime, I can actually complete the rectangle simply by connecting them. And there we go. This rectangle, that is rectangle K prime, L prime, M, N prime, sort of a strange name, has been scaled. Notice it's twice as long. It's twice as high as the preimage. Of course, maybe my drawing's not perfectly to scale, but hopefully you get the idea. Let's take a look at another example. In this one, the preimage and the image are both in the diagram already. They've already been given to us. This just tests our understanding of how these things work. It says triangle ABC is the preimage of triangle FDE. Determine the center and scale factor. The easiest thing to do is begin to identify the rays that contain the images and the preimages. Now, let me just say a couple things about this. First of all, this is not the best example in the world, and you'll have to forgive me for that, because it would have been better if we had called this ABC and A prime, B prime, C prime, only because it would make things easier. But just because the points get different names, it doesn't mean it's impossible. It's just we need to work with a different paradigm. We need to work with a different standard of nomenclature here. We know that point A corresponds to point F. Let's just tackle that first. Point A and point F are here and here. Now, we know that an image and a preimage of a point always lie on a ray, and that the endpoint of the ray is the center. Okay, so right now when we look at A and F, we don't really know where the center is. We haven't been told that. It's something we need to figure out. But we do know that these 2 points lie on a ray. So we can begin to draw the line on which they lie. And we can be sure that that ray is somewhere on that line. The ray we're looking for is somewhere on that line. Now, in order to find the endpoint, and by doing so find the center, we simply need to do the same process with points B and D, because B corresponds to D. So BD is also on a line, and that line looks something like this. And we know that C corresponds to E, so those are also on a line. And that line looks something like this. And so now you actually see what we have done is we have created a point of concurrency where all 3 of those lines cross. That point of concurrency is our center. It's the endpoint of the 3 rays. So if we clear the picture up again, this point, which I will call point O, it's the origin in this case, is the endpoint of ray OF, ray OD, and ray OE. There we go. So determine the center. The center is point O. We've named it point O. And its value in the coordinate plane here is 0, 0. Okay, now let me just pause here and say that this is no great coincidence. In fact, that's one of the reasons I chose this image. In dilations in geometry, almost always, almost invariably, the origin of the coordinate plane is set as the center of the dilation. I'm not saying that's always the case, but it almost always is the case. In fact, in lots of texts, the default center of dilation is the origin, and there are a couple of reasons for that. Number one, it's just easier to standardize, but number two, it makes calculating the values and the coordinates of the points very easy if my center is at 0, 0, because mathematically 0, 0 is just very easy to work with. Okay, the next thing we need to do is find the scale factor. To find the scale factor, one of the easiest ways to do that is to find some segment in the image and compare that in the form of a ratio to some corresponding segment in the preimage. So in this case, what I will do is we'll grab this segment OF, and we will compare that to the length of segment OA. OF over OA. And when we do that, we'll know what the scale factor is. So OF is a distance in here. F is the 0.12. I think you can see A is the 0.24. And so in order to find OF, we need the distance formula. So we'll know that it's the square root of, and we'll take the x value here in F. It's 1 minus 0. We need to square that. Plus 2 minus 0. And we need to square that. That's the distance from O to F. We'll divide that by the distance from O to A, which is 2 minus 0. And then we have 4 minus 0. Okay, simplifying that all up a little bit. In the numerator, we have 1 minus 0, which is 1 squared, that's 1. And we have 2 minus 0, which is 2. Squared is 4. And then in the denominator, we have 2 minus 0, which is 2. Squared is 4. Plus 4 minus 0, which is 4. Squared is 16. So we end up with the square root of 5 divided by the square root of 20. Now the square root of 20 in the denominator can actually be simplified. The square root of 20, of course, is the square root of 4 times 5, which is equal to the square root of 4 times the square root of 5. And of course, the square root of 4 is 2. So we have square root of 5 divided by 2 times the square root of 5. Well, the square root of 5 in the numerator cancels with the square root of 5 in the denominator. And so we end up with the number 1/2. 1/2 is our scale factor. We could go back to the picture and just begin to ask the question whether that seems logical and makes sense. Triangle ABC was our preimage, and triangle FDE was our image. So if we ask the question, what did we multiply ABC by in order to produce FDE? I think you can see that 1/2 is a reasonable number. Remember, a dilation does not necessarily result in a larger image. It could be a smaller image as well. The important thing is that the shape stays the same. That's everything we need to cover on dilations. As always, I encourage you to work through a few review problems on your own, and if you have any questions, send me an email.